So we're going to start off with, they're back. We're going to start off with a nice simple integral here. So this is, remember, this is our integral sign, the little squiggly s. So it's just telling us that we're doing that limit in that summation. And we are going to evaluate the area underneath the curve, 3x. And I understand that 3x is not a curve, it's just a straight line, but that's what we call a curve. Anything's a curve. And we're going to evaluate the area underneath that from 0 to 2. Okay? So that's our goal. So before we even get started, I just want to real quickly, we're just going to draw this. That's not through the origin. That's also not through the origin. That's better. All right, so here's our line, y equals 3x. Everybody good with that being y equals 3x? Pretend that's the slope of 3 there. And we want the area from 0 to 2. So this must be 6 units up, right? If this is 1, 2, this is 3x, so that must be 6. Everybody good with that and agree with that?
Yes.
Yes.
So what we're looking for then is just the area of, in this case, this triangle. True? Yeah?
Yeah.
Okay. Now, before we even bother to do that using our limit and our integral, I would hope that you should be able to just tell me what that area is, right? I mean, it's just a triangle, right? What's the area of that triangle? Should be 1/2 of the base, which is 2 times the height, which is
6.
6. So we should just get 6. Okay. Obviously, that's very easy, right? You should all be able to find the area of that triangle. The point of this problem is not to find the area, it's to understand how this integral works and how this limit and this summation works. So when we go through and do all this other work that we're doing, we had darn well better get an answer of 6 in the end. And so that's our goal, is to go through and do all this work and get an answer of 6. Okay? Because when we get into some other ones where we can't, I mean, if I give you a linear equation, you should be able to just use some geometry to figure out. But if I give you a parabola or a sine curve or 1/x, you're not going to be able to just use geometry to figure out that area. So we're going to do the easy ones where we could use geometry to check our work, and then we're going to move on to some where it's a little more difficult. Sound good? I'll take your silence to yes. So anytime we're looking for an integral, for now, we're going to turn it into this limit. And so if you're looking back at your notes from yesterday, you'll note that any of these integrals should be the limit as n approaches infinity of the sum from k equals 1 to n of f of x sub k times delta x, right? That's the limit and the summation that we came up with, that we said that should sum together the areas of all the little rectangles that I could draw within here to find the exact area underneath the curve, right? Everybody remember doing that and remember conceptually that that's what we were doing?
Yes.
Okay, cool. So we know what the limit, we know what a limit is, right? And we know how to do a limit as we go towards infinity. We understand what a summation is now, a little bit at least, hopefully. But we don't know what delta x is, and we don't know what x sub k is, right? So we know what f of x is. F of x is 3x, but we need to figure out what x sub k is and delta x. And so I'm going to give you guys, first off, delta x. Delta x is always equal to b minus a over n. We talked about that yesterday. It's equal to the ending point of our interval minus the starting point of our interval divided by n. So in this case, that will be 2 minus 0 over n, or 2 over n. And delta x will always, 100% of the time, equal b minus a over n. Everybody good with that?
Yes.
Okay, cool. The next thing then that we need to figure out is what is x sub k? Okay, And so x sub k is just how far over we're going each time to make our rectangles as we draw them underneath this curve. So what I'm going to do is I'm going to start off by just drawing a bunch of rectangles. And I'm just going to draw right rectangular approximations here. It doesn't matter how many I draw. It looks like I've drawn 5 of them. Okay. And so the x sub k is how far over I go for each particular rectangle. So x sub 1, the first one, would be how far over I went for the first rectangle's height. So how far over do I go from here, from the origin, to this point where I drew that first rectangle? What is x sub k? It's just the width of that rectangle, right? Or it's the width of one subinterval. Would you guys agree with that?
Yeah.
So what is the length of one of these subintervals?
2/5.
Well, in this case, it's 2/5 because I drew 5 of them. But remember, we're drawing in of them. I just happen to only be able to get 5 of them in there. But really, n is going towards infinity, right? We have an n number of them. So each of them has a length of 2 over n. So our x sub 1 is just 2 over n. Okay, so suppose I had 100 of them in here. That x sub 1 would be 2 over 100. If I had 500, it would be 2 over 500. I have n of them, so it's 2 over n. You're right in saying it's 2 over 5 for the picture I've drawn, but let's just say there are n rectangles.
I have a question.
Yeah,
What's the difference here between delta x and x sub k?
so delta x is the width of any one of these rectangles, and x sub k is how far we have gone over from our starting point to get to the kth rectangle. So,
Okay.
so delta x is just the width of any one, and those should all be the same. But x sub 1 is how far we went to get to the first one. X sub 2 will be how far we've gone to get to the second one, x sub 3 to the third. So x sub k is how far we've gone to get to any arbitrary kth rectangle. Does that make sense?
Yeah, thank you.
All right, so x sub 1 was our distance from the origin to the first rectangle. So what about x sub 2 then? How far did we go from the origin to the second rectangle? We went over the width of one rectangle, and then we went over the width of another rectangle, right? Which would be 2 over n times
2.
2, right? We go over 2 over n, right? What about to get to the third rectangle? How many times would we have to go over 2 over n?
3.
We'd have to go 2 over n 3 times. What about to get to the fourth rectangle? We have to go over 2 over n how many times?
4.
4. What if I wanted to go to the arbitrary kth rectangle? How many times would I have to go over 2 over n?
K times.
I have to go over k times. So we can see that x sub k is equal to 2k over n. Everybody good with that?
Oh, wait, but for x1, doesn't n just equal to 1? So then 2 over n would be 2 when like x1 it only went over 1 time so far.
Right, 2 over n times 1, which is 2 over n.
Wait, but doesn't n equal to 1, making 2 over
Nope, n does not equal 1. N is the number of rectangles.
Oh,
And I have more than one rectangle there. In fact, I am going to have eventually an infinite number of rectangles there. Remember, this picture, I can't draw an infinite number of rectangles, so I've just drawn however many I could fit in there to look at.
Oh.
But we are working under the assumption that there are an infinite number of rectangles drawn underneath that curve, or really drawn attached to that curve because they're sticking
So
out.
since x represents like the number, the distance you already covered as a whole, like I'm assuming n then just equals to 2 at the time then, right?
I'm not sure what you just said or what you meant.
Like x sub k, since it covers like the distance, yeah, like from the origin to the distance it covered as a whole so far, like
Yes, the x sub 1 is the distance from the origin to the first rectangle. X sub 2 is the distance from the origin to the second rectangle. Because remember, an x value is always a distance from the origin to the right or to the left, right? So all of these x sub 1, 2, 3, 4, x sub k's, they're all distances from the origin, because that's what we have to plug into our function. We have to find f of x sub k to find the height of the rectangle, right? So the width of the rectangle is the delta x of each one. The height of each one is f of how high up, f of how far over we've gone from the origin.
So then just to clarify, that means like the value of n is 2 then, at least at the time?
No. N is the number of rectangles, which is always infinite. N always represents the number of rectangles that we are drawing underneath the curve, which will always be an infinite number of rectangles for any of these integrals, because that's how we get the exact area, is by having an infinite number of them.
Wait, but then how does it make x sub 1 equal to 1 then?
X sub 1 is not equal to 1. X sub 1 is equal to 2 over n times 1, or just 2 over n.
But then
X sub 1 is the distance from the origin to go up that we need to go to get the height of that first rectangle. So we went over the width of one rectangle, which is 2 over n.
Oh.
Because the entire interval is 2, and we have n subintervals, so the length of each subinterval is 2 over n. So the first rectangle has a height of f of 2 over n. So we need to plug 2 over n in to our function to find that height.
All right.
Does that make sense? Maybe so this is our height. This is the width of each. So the height, or sorry, the width of each one, width of each rectangle, and each of those widths, they're all the same, right? Delta x doesn't change for each rectangle, but the heights, these are all different. So x sub k changes, right? X sub 1 is different than x sub 2 as I go up from 1 to n, right? X sub 1 is different than x sub 2 is different than x sub 3. So we have different heights because each of these rectangles have different heights. And so we're finding the x value to plug into our function 3x that tells us the height at each of these different rectangles, at each of these, infinite number of rectangles.
Oh.
Does that make sense?
Yeah.
Any other questions on that, anybody? Okay. So we found x sub k, and we found delta x. And so now what we want to do is we want to take those and we want to plug them into this original limit. So we're going to say this limit is now equal to the limit as n approaches infinity of the sum from k equals 1 to n of f of x sub k. Well, f of x is 3x. So 3 times x sub k, which is 2k over n. And then times delta x, which is 2. So does everybody see what we've done there?
Yeah.
Right, this, and I'm going to write this maybe separately here. This f of x sub k, that is our height. That's 3x sub k, because f of x is 3x. So this is 3x sub k, which is now 3x sub k delta x. So I'll even write it below 3 x sub k delta x. Everybody good there or no?
Yes.
Okay. And so now I'm gonna, there's a little bit we need to say here is that first off, most of the time on the AP test, this is as far as they will ask you to go. Most of the time. Okay. Sometimes they will ask you to go through and simplify this, like in a multiple choice, or sometimes they may ask you in a free response to go through and actually evaluate this all the way out. So we're going to learn how to do that also. It's very rare that they ask that, but it's part of the curriculum, so we need to make sure that you guys can do it. But most of the time, this is where they will stop. Okay? So, and we're going to do a bunch more of getting them to this form, but we're going to finish evaluating this. So this is now a limit as n approaches infinity of a sum from k equals 1 to n. And what do I get if I simplify all of this out? If I multiply all that together, I should get 12k over n squared. Do you guys agree with that?
Yeah.
Good. So my next question then is, within this summation, are there any constants?
N is a constant, yeah.
Yes, n is a constant. So like once we talk about n being part of the limit, it's no longer a constant, but just within the summation, n is a constant. And what else is a constant? Isn't 12 a constant?
Yeah.
Yeah, 12 is also a constant. K is not a constant, right? Because what is K doing? K is increasing. It's going from 1 to 2 to 3 to 4 to 5. And it's increasing. It's the variable. K is the variable within this summation. So what did we talk about yesterday? If we had a constant inside of a summation, what could we do with it?
Take it out and put it in the front.
Right. And so this 12 over n squared is a constant. So I can take this limit as n approaches infinity of 12 over n squared times the sum from k equals 1 to n of k. And from there, yesterday we had a formula that would evaluate for us what this was, right? We proved that the sum of all of the integers from 1 to n was what?
N times n plus 1 over 2.
Exactly. So this piece right here is n times n plus 1 over 2. So we're going to replace this with n times n plus 1 over 2. And then all we'll have left is just our limit. So we're going to have a limit as n approaches infinity of 12 over n squared times n plus 1 all over 2. And now we've gone from having a limit with a summation, with a function, with an x sub k and a delta x, into something that was just a limit and the summations with k's and n's, into something that is now just a limit. And a limit should be easy for us to evaluate. Okay? Let's simplify out what we've got inside of the limit first. The limit as n approaches infinity of, well, let's see, n times n plus 1 is n squared plus n. So this becomes 12n squared plus 12n over 2n squared. And how do we find the limit as n approaches infinity of that rational function?
Since n's, I don't know, since like the highest polynomial is equal for both numerator and denominator, you can just remove just 12n, like the second one, and then divide n2 over n2 and then by 12 by 2, and then you get 6.
Exactly. So it's a rational function, and the degree of the numerator is equal to the degree of the denominator. And so this is just like finding a horizontal asymptote to the right. You just divide the leading coefficients and you get 6. Alternatively, you could factor out an n and cancel if you wanted to, and then simplify that way. Or you could use L'Hopital's rule because it's infinity over infinity. But if you recognize that this is a rational function with the same degree in the numerator and denominator, just divide the leading coefficients and get your answer. And that's how these will always end up as, for the ones we're going to do, they'll always end up as just rational functions where you can divide those leading coefficients. So that'll make life pretty easy. And we'll note that the value we got was 6, which is exactly what we said we should have got, right? Should have got 6, and we did. Good or no?
Good. Oh, wait. Actually, one last question. If we're trying to determine the height, if x sub k is like to determine the height, but then like n always equals to infinity, wouldn't that just make it equal 0 though?
Well, that was the whole point, was to make it 0, but not 0 because we're taking the limit. We're getting very, very close to this width being 0 of each of the rectangles because we're having an approach infinity, but it's not actually infinity. So we're looking at the behavior as we get very, very, very large.
Oh,
As we get a large number. So that's kind of what we talked about yesterday, right? It's like we'd be dividing by 0 because effectively there's a width of 0, but we can't have that, so we get around that by doing the limit.
all right.
Does that make sense?
Yeah.
Anybody else have any questions on this first one? Because we're going to do some more of these. Make sure you guys have it down. All right, so we're gonna move on to this one next, the integral from 1 to 4 of 4x dx. So take a second, sketch the graph, and sort of draw some right rectangular approximations on that. Give me 1 second. Okay, sorry. All right, so did you guys sketch y equals 4x? From 1 to 4. So this time what we're looking at here is a trapezoid, right? If we're just looking for the specific area underneath this curve.
Yeah.
It's just a trapezoid. So what's the area of that trapezoid? How do we find the area of a trapezoid? Just so we know what number we're hoping to get in the end. Should be base 1. What's the first base?
1,
No.
4,
4 plus the second base, which is
16.
16 divided by 2 times the height, right, which is 3. So what should we get in the end here with any luck? We should get 30, right? That's what we should get. All right, we know what the answer is to this problem. So let's see if we can correctly do this. So first off, every time we do one of these, the first thing that happens is we write it out as a limit, because n approaches infinity, of the sum from k equals 1 to n of f of x sub k. So that's going to be 4x sub k times delta x. And that's not going to change. The only thing that'll change is what my function inside of there is, right? It's always f of x sub k. So in this case, that was 3x sub k. In this case, it's 4x sub k. Everybody good with the first step there?
Yeah.
Okay. So now let's figure out what's delta x. Delta x is always equal to b minus a over n, which in this case will be
3 over n.
4 minus 1 over n or 3 over n. And then we need to figure out what x sub k is, right? So x sub k can easily be found by starting with x sub 1 and just looking for a pattern. So the first place we're at where we go up for a rectangle is x sub 1. So how far over have we gone from the origin to get to x sub 1?
One plus 3 over n.
Right, we've gone over 1 unit, right, to go from 0 to 1 to where we're starting our interval. And then we've gone over the width of one rectangle, which is 3 over n. So what about to get to the start of the second rectangle? How far do we go from the origin? We have to go over 1 again, right? And then we've gone over the width of 2 rectangles, which would be 3 over n times 2. And you probably notice that this pattern is going to continue. X sub 3 will be 1 plus 3 over n times 3. And what about x sub k?
3 over n times k.
3 over n times k, or just 1 plus 3k over. All right, so we've got our delta x value, and we've got our x sub k value. Everybody good with that? Any issues there? Okay, so we've now got the limit as n approaches infinity of the sum from k equals 1 to n of 4 times x sub k, which was 1 plus 3k over n, times delta x, which was 3 over n. Everybody good with that? Any questions on that? And as I said before, most of the time, they'll just let you leave it right here, but we're going to evaluate all these out just to make sure you know how to do it. So we'll simplify everything within the summation first. So we've got 4 times 3 over n is 12 over n that we're going to distribute to both pieces of this. So 12 over n times 1 will just be 12 over n. And 12 over n times 3k over n will be 36k over n squared. Everybody agree with that?
Yeah.
All right. So now, depending on how comfortable you feel with summations, you can either just evaluate this summation right now, which you probably don't feel comfortable enough to do that, or we can separate it into 2 different summations, which I think will help everybody to sort of conceptualize this. So we're going to do the limit as n approaches infinity of the sum from k equals 1 to n of 12 over n, plus the sum from k equals 1 to n of 36k over n squared. Right? Because one of the things we talked about yesterday was that if I had a summation of something plus something else, I could do them separately. So what can you tell me about 12 over n within the context of the summation? Is 12 a constant?
Yes.
Is n a constant?
Yeah.
Solely within the summation? Yeah, yes it is. So this is just a constant. So I'm just summing together a bunch of 12 over n's. How many 12 over n's am I summing together?
An infinite number.
I'm summing together from 1 to
N.
n, right? So if I take, let's say if I have a 7 in here, what would I get? I'd get how many 7s?
N sevens.
Which would be 7n, right? Well, I don't have 7 in there. I have a different constant. I have 12 over n in there. So how many 12 over n's do I have?
N of them.
I have n of them, right? 12 over n times n. And then what about over here? The k can turn into what? Since it's a sum from k equals 1 to n of k, this constant that we had can go out into the front, and what's k become? What's the sum from k equals 1 to n of k?
N times N plus 1 over 2.
Times n plus 1 over 2. And so now we should be able to simplify this down. We have the limit as n approaches infinity of one rational function, 12n over n, plus another rational function, 36n squared plus 36n over 2n squared. And we'll note that in the first one, the degree is the same. And so what does the first part of that become?
Twelve.
12. And what about the second part? Since the degree is the same, the highest degree is the same, you divide the leading coefficients, 12 plus 18, and that ought to give us 30, just like we said it should be. Good or no?
Good.
We getting the hang of it a little bit or no?
Slightly.
Slightly. All right. Let's make it slightly more complicated by adding an extra number in there, but not really all that bad. 2x plus 2. So we're going to integrate that, find the area under the curve of that from 0 to 3. So I'm just going to sketch 2x plus 2. It doesn't really matter, just as long as it was above the origin there, right? This is y equals 2x plus 2. We're going to go from 0 to 3. And that's just a trapezoid, right? So this time, let's not know what we're going after. Let's just figure out what it is and see afterwards if the geometry tells us that the area of the trapezoid is the same as what we got. So first step will always be to just sketch out these right approximations. So I sketched out a bunch of those. And this should become a limit as n approaches infinity of the sum from k equals 1 to n of f of x sub k, so 2x sub k plus 2 times delta x. Everybody good there?
Yeah.
All right. What is delta x for this one?
Three over N.
3 over n. And what is x sub k? So let's think about x sub 1. I'm not necessarily going to write them all out this time. X sub 1 should be the distance from the origin to the first rectangle's height. That's where we go up from to find the first height of the rectangle. So what's x sub 1?
3 over n.
And x sub 2?
6 over n.
Right, 3 over n times 2, right, or 6 over n. X sub 3 will be 3 over n times 3. So what will x sub k be?
3k over n.
3K.
3k over n, or 3 over n times k. And so we should be able to immediately plug all that in. We've got the limit as n approaches infinity of the sum from k equals 1 to n of 2 times x sub k plus 2 all times delta x. And once again, this is probably as far as they're going to make you simplify it, but we will go all the way through just to make sure we're good with it. So we've got 2 times 3k over n is 6k over n plus 2. If we have 6k over n times 3 over n, that ought to be 18k over n squared. And then this one ought to be plus 6 over n. Good or no?
Yeah.
Okay. And then once again, the 18 over n squared is a constant. So we're multiplying that by the summation of k, which is n times n plus 1 over 2. So 18n times n plus 1 over 2n squared. Oops, I forgot to write my limit. 6 over n, which should be what? When I have n of those that I'm summing together, that should be 6 over n times should be 6 over n times what? I'm adding together how many of them?
N.
N of them. So 6 over n times n. And now we'll note that this is just a rational function. All right, 18n squared plus 18n over 2n squared. And then this one is another rational function, 6n over n. So what does the first part of that become? As we find that limit.
9.
And the second part of it?
6.
Which should give us 15. Good or no?
Good.
All right, let's check and make sure we get this same value if we actually find the area of the trapezoid. So what's the first base? If I start at 0, how high do I go up?
2.
2. And the second base, if I start at 3, 3 times 2 is 6, right? Plus the 2 is 8. Divided by 2 times the height of the trapezoid, which is 3. And what does that give us? 10 over 2 is 5 times 3. It is 15. So it looks like it worked out, yeah? Good or no?
Good.
All right. One more of these before we get into some that we can't check geometrically. So I'm going to let you guys work through this one on your own. But before I let you do that, we're going to figure out what you should get as your answer. So 3 minus 2x is going to look something like this. Probably should be a little steeper than that, more like that. And we're going to go from, now actually, let's not figure out what this is right off the bat. Let's just have you guys work through it and see if you can find the value of this integral. You guys think you can do that?
Yeah.
Or no? All right, I'm going to give you guys, I don't know, what do you think? 4 or 5 minutes ought to be enough? Yeah?
Yeah.
All right, I will give you guys 5 minutes to do this, and then we'll work through and make sure you guys did all right together. Ready to go? So first off, you should have written this out as a limit as n approaches infinity. Your sum from k equals 1 to n of f of x sub k times delta x. And you decided,
Wait. So k is always equal to 1 instead of like not 2.
For doing this, yes.
Oh, okay.
I mean, you can do a summation from k equals 2 to whatever, or from k equals 100 to whatever. you don't have to start at 1, but we are starting at always the first rectangle that we draw. So it's k equals 1.
Right.
So what do we get for delta x? Should have got 2 over n, right? 4 minus 2 over n.
Yeah.
And then what did you get as your x sub k value?
1 plus 2k over n.
I don't think it should have been 1 plus 2k over n. It should have been 2 plus 2k over n. Because where are we starting this interval?
2.
At 2, not at 1. So we always go over those 2 units first, and then we go over that 2k over n. Everybody good with x sub k being 2 plus 2k over n?
Yeah.
Anybody have a question on that? And I'm going to give you this formula right now. You'll probably note that this is true from everything we've done so far. X sub k is always equal to a plus k times delta x. So if we go back and look at all of them that we've done real quickly, right here we had x sub k was 3k over n, which was a 0 plus k delta x, right? K times 3 over n. And if we look at this one, our x sub k was a 1 plus k times delta x. And same here, our x sub k was a, which was 0, plus k times delta x. So that's what that will always equal. So this will be helpful for you to memorize, that delta x is b minus a over n, and x sub k is a plus k delta x. Everybody good there?
Yeah.
All right. So this becomes the limit as n approaches infinity of the sum from k equals 1 to n of 3 minus 2 times 2 plus 2k over n times 2 over n. And if we distribute all this junk through, this becomes 3 minus 4, right? If I do the minus 2 times the 2. So that's a negative 1 times the 2 over n. So that's, oops, almost forgot my summation. The 3 minus the 4 is negative 1 times the 2 over n is negative 2 over n. And then we have a negative 4k over n. So that becomes negative 8k over n squared. Is that what you guys had inside of your summation?
Yes.
Cool. And then we evaluated the summation. The negative 2 over n was a constant, so we had n of those, so that's just negative 2 n over n. And the minus 8k over n squared, the minus 8 over n squared was the constant, so the k just becomes n times n plus 1 over 2. And now we have a rational function over a rational function, divide the leading coefficients, and we get negative 2 minus, and then 8n squared over 2n squared is a minus 4. So negative 2 minus 4 is negative 6. Good or no?
That negative 6 is an area, so
Yeah, so that's what I was hoping somebody might mention. Why is that an area? That's weird, right? So the reason that that happens is this was what our function looked like, 3 minus 2x, something like that. Well, at x equals 2, what's the value? The value is already at negative 1. So here's 2 and here's 4. So we'll note that all of this that we would have been looking for is actually below the x-axis. Everybody see that that's all below the x-axis?
Yeah.
And so what an integral actually does, and so we've only been talking, oh, it finds the area under the curve. Well, what it does is it finds the area between the curve and the x-axis. Anytime that space is above the x-axis, it comes out to be positive, and anytime that space is below the x-axis, it comes out to be negative. That's something we're going to talk a lot more about when we get a couple units away from now. For right now, we're just kind of talking about finding an integral or finding this area. So the value of an integral can be negative, even though you can't ever have a negative area. So later on this year, we're going to make a distinction between the area and an integral itself. But for now, just be good with the integral's value is -6. And so like if we had one where part of it, like suppose this was from 1 to 4, part of it would be above the x-axis and part would be below. And so the part above would be positive and the part below would be negative, and they would sort of cancel each other partially out. But we'll, like I said, we'll talk much, much, much more about that when we do a bunch more stuff with integrals later on this year. So hopefully for now that answers the question about why that can be negative.
By the way, I forgot to ask this earlier, but how does k grow to be equal to n plus 1 again?
When you sum together all of the k's from 1 to n, it comes out to be n times n plus 1 over 2. That was a formula that we proved yesterday.
Yeah.
Right, we wrote it out 1 plus 2 plus 3 dot 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 all the way up to n, and then we wrote them backwards and added them together. Remember doing that?
Yeah.
Yeah.
Mm-hmm.
But yeah, that's in yesterday's notes. So if you want to take a look at it again, it's in there in the video or in the.
Oh yeah, and then how does it turn to 2n times 2? Do you like multiply both?
You mean the 2n over n right here?
Yeah. Well, and then also the denominator, the second one.
Well, the formula for k, like I was just saying, is n times n plus 1 over 2. So that's where the 2 comes from. And then this summation just says add together n of these things. So n -2 over n's is -2 over n times n. Right. If I'm adding together a bunch of numbers that's the same number every time, -2 over n plus -2 over n plus -2 over n times, it's -2 over n times n.
All right.
I don't see yesterday's notes posted.
I'm almost positive I posted them. I can check. I mean, I know for sure that the video is up, but I'm almost positive I put the notes up too.
I could be wrong, but I see the only one I see is from the latest I see is.
I got them. They're in there, January 4th, 21. They're up. Maybe you need to refresh your Google Drive or something, but they're definitely up.
Yeah, I'll try it a few times.
If not, just send me a reminder and I can send you the link to it. But they're definitely there. All right, we got 10 minutes. Let's see if we can do 2 more of these and be done with them. So this one we can't check geometrically because now it's a parabola, right? So we're going to look for the limit as n approaches infinity of the sum from k equals 1 to n of 3x sub k squared times delta x. And off to the side, let's figure out what delta x is. What's delta x going to be?
Two over n.
2 over n. And what's our x sub k? Using that formula, a plus k delta x. A is 0, right? So it's just 0 plus k delta x, 2k over n. Everybody good with that? Yeah. Okay. So now we'll just plug those in. The limit as n approaches infinity. The sum from k equals 1 to n. 3 times x sub k squared, so 3 times 2k over n squared times delta x, which is 2 over n. And then combine everything in the summation together. 2k over n squared ought to be 4k squared over n squared. And 4k squared times 2 is 8k squared times 3 is 24k squared. And then in the denominator, it should be n cubed. Yeah? Good or no?
Good.
Okay. And now, yesterday, I told you another good one to know would be the summation for k squared. What's the summation for k squared? It's n times
N plus 1.
n plus 1 times
2n plus 1.
2n plus 1 all over 6. And so we will just replace that k squared with that, and that will take care of the summation. So now we have a limit as n approaches infinity of 24n times n plus 1 times 2n plus 1 all over 6n cubed. And
You get that 24 again?
2 squared is 4, times the 2 is 8, times the 3 is 24.
Oh, and then the squared stays because k is squared.
Yeah.
Thank you.
Yep. And so now we'll note that the degree of the numerator is we've got n times n times n, so n cubed. Right? And down here we also have n cubed. So I'm just going to sort of, if I do 24 times n times 2n, that's going to be a 48 n cubed plus some other stuff that's less significant than that over 6n cubed, and it's a rational function. And so we just divide the leading coefficient since the degree is the same, and we get 8. And so that's telling us that the area underneath the parabola 3x squared from 0 to 2 is exactly 8 units. Good or no?
Good.
All right. One more. The integral from 1 to 2 of 1 minus 6x squared dx. So we'll start off the same way we've been doing all of them, with our limit as n approaches infinity of a sum from k equals 1 to n of 1 minus 6 x sub k squared times delta x. And then we need to figure out what delta x is and what x sub k is. So what's delta x?
1 over n.
1 over n, right? 2 minus 1 over n. And what's x sub k?
One plus k over n.
1 plus k over n, exactly. And so we'll just plug all that in. And this time the algebra is going to be a little bit of a pain, but it could be worse. 1 minus 6 times x sub k squared times 1 over n. And let's see if we can do this in only a couple of steps here to simplify. So it's going to be 1 minus 6 times 1 plus k over n squared, which will be 1 plus 2k over n plus k squared over n squared if we distribute that out, times 1 over n. And let's distribute that 1 over n through everything. So first off, we have a 1 minus a 6. That's a negative 5 times the 1 over n, so negative 5 over n. And then we have a negative 6 times the 2k, so that's negative 12k over n times n, so over n squared. And then we have a negative 6k squared over n squared times n over n cubed. Everybody good with that?
Yeah.
And now we just do each of these summations. So the first one is a constant. So I have n of those constants, so negative 5n over n. The second one has the k in it, so that becomes negative 12n times n plus 1 over 2n squared. And the last one has a k squared, so negative 6n times n plus 1 times 2n plus 1 all over 6n cubed. And that's just replacing the k with an n times n plus 1 over 2 and the k squared with an n times n plus 1 times 2n plus 1 over 6. Now we do our limit. Each of them is a rational function, so the degree is the same for each of them. Negative 5n over n just gives us negative 5. This one becomes minus 12 over 2. And this one becomes minus 6 times 2 is 12 over 6, so minus 2 more. And that one comes out to be negative 13. Good or no?
Good.
Any questions on that or anything else from today?